Now acceleration is meter per second square, that is L into t to the power minus 2 into time. So the second part will again become L into t to the power minus 1. So as we see here, both in the right hand side and the left hand side of this equation, the physical quantity are having the dimensional formula of L into t to the power minus 1. Now we'll see how to convert one system of units into another. If the dimensional formula of a physical quantity is m to the power a, L to the power b and t to the power c, and its derived units in the two systems are say m1 to the power a, L1 to the power b and t1 to the power c, and m2 to the power a, L2 to the power b and t2 to the power c, then we can write n1 into m1a, L1b, t1c is equal to n2 into m2a into L2b into t2c. Now in this way we can find out the value of n2 for a given n1. For example, suppose we want to convert 1 Newton, which is the SI unit for force, in CJ system. Now in CJ system the unit for force is dyne, that is dyne. Now we want to find out how many dyne is equal to 1 Newton, or how many dynes are there in 1 Newton. So suppose in SI system the dimensional formula for force is mlt minus 2. So in SI system we can write n1 into kilogram into meter into second square is equal to n2 into gram into centimeter into second square. So n2 will be equal to n1 into kilogram into meter into second square by gram into centimeter into second square. So suppose n1 is 1, that is we are taking 1 Newton. So n2 will be equal to, now 1 kilogram will have 1000 gram, that is 10 to the power 3 gram, and 1 meter will have 100 centimeters, that is 10 to the power 2 centimeters. So we can write 10 to the power 3 gram into 10 to the power 2 centimeter into second square. Now we can cancel out gram, meter and second square from denominator and numerator, so we are left with 10 to the power 5. So this is the value of n2. So we can say that 1 Newton, which is the SI unit of force, is equal to 10 to the power 5 dyne, which is CGS unit for force. Now there is another use of dimensional equation, that is to check the correctness of a physical relation. So dimension of all the terms on the two sides of an equation must be the same. So this is the concept that we use to find out whether a physical relation is correct or not. So suppose for example a relation is given, v is equal to ut plus at, where v is the velocity, u is velocity, t is time and a is acceleration. Now we'll see what are the dimension of various physical quantities on both sides of this equation. So v is velocity, that is meter per second, so we can write it as L into t to the power minus 1. Similarly, u is again velocity, so we can write it as L into t to the power minus 1 into time, which is t. Now acceleration is nothing but meter per second square, that is L into t to the power minus 2 into time, which is t. So on the left hand side we have L into t to the power minus 1, and on the right hand side we have L plus L into t to the power minus 1. So we can see that the dimension of V, that is L into t to the power minus 1, matches with the second term on the right hand side, that is 80, but not with the first term on the right hand side. So since the dimension of all the terms on the two sides of an equation must be same, we can say that this particular physical relation is not correct. Now let's talk about the limitations of dimensional analysis. The dimensional analysis gives no information about pure numeric and non-dimensional constants. It gives no information about the dependence of a physical quantity on trigonometric, exponential and logarithmic function. If a physical quantity depends upon more than 3 physical quantities, then dimensional analysis cannot be used to derive their relationship. And this method gives no information about dimensional constants such as universal constant for gravitation, that is G, and Planck constant, etc. Now we will start